What we are going to see is whether there is a Turing machine that can decide and the language recognized by another Turing machine is regular or not. Basically, if you want to say in some other way, whether can we convert a Turing machine to a finite automata or not. That is the thing. Like, is it decidable? This problem is decidable. We'll see that. Without wasting further time, let's get started and see what is decidable and these things are. So before that, what is Turing machine? Turing machine is a generalized model for any modern day computers. Anything that we can do with our modern day computers, we can also do with this Turing machine. So even though this mathematical model is such a powerful one, there are some problems which can't be solved even using Turing machine. Those are all called Turing unrecognizable. That's a topic for another day. So today what we are going to see is, even though the languages are Turing recognizable, some of them are undecidable. You see what is this undecidable means, and like why some languages are undecidable. So I'm assuming that you know about Turing machine and regular expression and like our regular language, which can be represented using regular expressions, and concept of reducibility. Even though like I'll slightly explain why, what is this reducibility. So I'll explain this about reducibility, but I'm assuming that you know about this Turing machine and regular expression. So here, before going to what is this decidable and undecidable is, we'll see two definitions. This particular language ATM is undecidable. What is this language? This language contains strings m, w, where m is a Turing machine and w is string accepted by m. So we can represent any Turing machine, any machine m as a string. That encoding, the notation here, that angle brackets is for that. The encoding of this Turing machine m, w is a string in this language ATM. So already using some diagonalization method, it has been proven that this language is undecidable. So that means there is no Turing machine yes such that it can decide this language. It can decide whether M accepts W or not. It can't decide. There is no such Turing machine yes. So this has been already proven. We are going to prove this one. Regular TM is undecidable. What is this regular TM language? This language contains a string encoding of M, where M is a Turing machine, and the language of M is a regular language. If the language of M is the regular language, then that M, encoding of M, is accepted by this regular language. That encoding comes under this regular TM language. So that means if this is not decidable, means there is no such Turing machine TMR that can decide whether this language whether M is regular or not. There is no such Turing machine that can decide this problem, that can say whether this M accepts or not. So we'll see what this decides and undecides means. So for example, take some Turing machine G which accepts W. The language represented by this Turing machine G is strings of strings. That string W contains 0. If the string W contains 0, that means that W is in the language recognized by this Turing machine G. So that means this 0010 will be accepted by this Turing machine G, and G111 will be rejected by this Turing machine G. Any string of symbols will be either accepted or rejected by this Turing machine. So this is decidable. But the two definitions seen here, these languages are undecidable. One is already proven, one we are going to prove. So we are going to use proof by contradiction. What this means is, we will assume something and come to the contradiction. For example, we are going to assume that TMR, there is some TMR exists which can decide regular TM, the language regular TM, and will come to the conclusion that there can't be such Turing machine R. So for that we are going to use concept of reducibility. Basically, what reducibility means, if there are two problems A and B, if we know the solution for B, we can construct the solution for A. That means we can reduce A to B. So the same concept we are going to use here. So if we are going to assume there is a Turing machine R that can decide the language regular TM. If such Turing machine exists, then we can use the Turing machine R to build Turing machine S, which is also going to be a decidable Turing machine, which is going to decide this ATM. But already we know that this can't be true, because there can't be such Turing machine S which can decide this ATM. So that has been already proven using this diagonalization method. So we will come to the conclusion that there can't be such Turing machine R. So regular TM also undecidable. So the thing is, first we'll see the construction of Turing machine yes. So this Turing machine yes will get the input m comma w, and first as of now think of this green text as a black box. Don't focus on this. This machine going to decide whether m accepts w or not. For that, if we try to directly use m on machine R, Turing machine R, then R will say whether m is regular or not. But we can't use that result to say whether m accepts w or not. We can't say that using directly inputting m to this R. For that only we are building this m2. Now we'll see how this m2 works. Basically, the core idea is m2 is going to be non-regular by default. It is going to recognize non-regular language. That is this 0 power n, 1 power n. There are a lot of non-regular language. This one we are taking 0 power n, 1 power n. By default, this Turing machine m2 is going to accept this 0 power n, 1 power n. But only when m accepts w, m on input w, and if that accepts w, then accept x. If x is equal to 0 power n, 1 power n, then accept it. That means like this is without this like if x equal to 0 power n and 1 power n, it is going to accept it. It is a non-regular language. So if m does not accept w, means this machine is going to only accept 0 power n and 1 power n, which is non-regular. We will see in the next in a minute that how this logic works. I'll just give a brief idea here. So if 0 power n, 1 power n is the only language recognized by this m2, that is going to be a non-regular. So if m accepts w, then it is going to accept all the strings x, If it is 0 power n and 1 power n, or any other strings of zeros and ones, all the things will be accepted by this Turing machine. Then this Turing machine m2 will become regular language. It will recognize regular language. How we'll see why this converted into a regular. We'll see in the next minute. As of now, know that like you should understand that if like m2 will be regular only when m accepts w. This m2 will recognize regular language only when m accepts w. So this is the case means, so we will run this m2 to this machine. We will give m2 as the input to the Turing machine R. If R accepts m2, that means this m2 is regular. Based on our discussion, m2 will be regular only when m accepts w. So that is the case means then m accepts w. So we will accept the input whatever m comma w. If that's not the case, if R rejects m2, that means this m2 is non-regular. m2 will be non-regular only when m rejects w. So that means we will reject the input. So this is the case. Like, so we are using this m2 as the input. Here the one thing you have to notice is, don't try to give some input x and try to run this machine. We are never going to run the m2 for some input. This m2 we are just going to use as an input to R. This R is going to do that work. Without running m, it is going to check that whether m2 is regular or not. If m accepts w, then it is going to be regular. If m does not accept w, m is going to be not regular. m2 is going to be not regular. So that this r will going to do that work. That's what is this r is going to do. So we don't want to run any input x to this machine. So we'll see why this 0 power n and 1 power n is regular. Then when m and input w, it converts into like initially like my mistake, like this x 0 power n and 1 power n is a non-regular, and only on input m accepts w, this whole machine going to recognize regular language. How it is going to be converted like that, we'll see. And this m and w is like a constant here. So this Turing machine m2 will not like will not going to be like becoming regular or non-regular at runtime. Based on this m and w input, it is either going to be regular or non-regular. When it becomes regular, it is not going to change. When we know the input m comma w, it is going to be finalized whether m2 is regular or not. This m comma 2 is not input to this tm m2. It is part of the definition. This m and w is a part of the definition. So the next thing is, why 0 power n and 1 power n is not regular? Because we can't construct some like deterministic finite automata that can accept this language 0 power n and 1 power n, because deterministic finite automata doesn't have any memory, so it can't remember how many zeros are in here to so it can compare with 0 power n and 1 power n. So this is not a regular. And then how it becomes regular once this has been evaluated? Like if m is m on input w, if m accepts w, this machine not only accepts 0 power n and 1 power n, but also all other strings x. All other strings means any possible strings x, 0 and 1 with 0 and 1. So 0 here I am assuming that the sigma is alphabets like input alphabet which contains only 0 and 1. So the sigma star is any string which can be formed using 0 and 1 will be accepted by this m2 when m accepts w. So this means once this m accepts w, this whole m2 is converted into regular language. It will recognize regular language, but this will not be like change at runtime, like runtime kind of thing. Like it is going to be decided as soon as we will define that machine. When we define that machine, because this m and w does not depend on this x, it is going to be always constant regardless of this x. So as soon as we define this m2, it is either going to be accept based on m like either going to be a regular if m accepts w, or non-regular if m rejects w. So that's why this m2 is like regular only when m accepts w. So we know these three whys, why these three are the cases. So now we can easily understand this final result, like how this make the contradiction. So this is the case. If we can build such Turing machine R, then we can pass this m2 as the input to the R, and R will say reject, either accept or reject this m2, because R is decidable. That means if it accepts m2, then m2 is regular. M2 will be regular only when m accepts w. If R rejects, then like this m2 will be non-regular. If R rejects m2, then m2 will be non-regular. M2 will be non-regular only when m rejects w. So if R accepts m2, then this m2 is regular. That means m accepts w. That means we can accept this m comma w because m accepts w. Otherwise we will reject. So such a way we can build Turing machine. Yes, this means, this implies that this Turing machine ATM is decidable, which is not true. This is undecidable. This is the contradiction. So there can't be such Turing machine, or there can't be any Turing machine, or that can decide whether some Turing machine M2 or any Turing machine is regular or not. So we have proven that testing whether a language is recognized by Turing machine is regular language or not is an undecidable. It is an undecidable. So that's it. Thank you for watching this video. If you want me to explain some more topics about this Turing machine and like deterministic finite automata or pumping lemma and this concept, please comment on this video. I'll try to make these videos. Thank you.